let us jump directly into this first problem or a project that is a good example to illustrate that data structures are all pervasive, right? So, so by the end of this example, I hope to impress upon you that even a very simple thing like arithmetic that we take for granted has some merit in trying to analyze what is going on inside the operations actually, right? Okay. So we will consider number systems, right? And what are number systems? These are simply a way to represent numbers. We all know several number systems. Let us say maybe the things we know are binary, decimal, etc. We'll come to that in a moment. But why are number systems important? Well, using the representation that is essentially the number system, one can also do arithmetic on numbers, right? And it is no surprise that if you think of advanced early civilizations like the Greek or the Roman or somebody, you will notice that essentially this ability to do arithmetic and to be able to count is an important trait in the civilization, right? I mean, without that you probably cannot do a lot of things actually, right? So that's very important essentially, right? And you would not be surprised to know that there are several systems that are dated to these early civilizations which are still in use today actually. Okay. Now, yeah, so let us list some known number systems in practice or even today. So this particular system called the Hindu system or the decimal system or the Arabic system, essentially several names are attached to it, but it is what we use every day. The digits are 0 through 9, and we know that a number like 43 will be written as 4 on the tens place and 3 on the units place, right? And many of us don't really relate to this, but it is popular at one point. So this is called as the Roman system, where you do not have any particular positional weights attached to positions, but you have a particular way of writing numbers. We'll see shortly. As computer scientists, we are more familiar with binary, octal, hexadecimal, these kind of number systems. Possibly because computers understand 0, 1 better than decimal numbers. There is a reason for that. That's not important now, right? Okay. So the unary system is something we may have used at one point or another, and we don't really think of it as a number system per se. But in my opinion, it deserves to be called a number system because it gives a way to do arithmetic just as any other number system, right? Okay. Now, one way to classify all these number systems is by considering whether they are positional or non-positional. What we mean by that is that in the system such as Hindu or decimal system or even binary system, there are these digits 0 through 9 in the case of decimal and 0, 1 in the case of binary, and every position has certain weight. So here the weight is 1, here it is 10, here it is 100, 1000, 10,000, so on and so forth. And here, for instance, this is 1, this is 2, this is 4, this is 8, and this is 16. These are the weights, right? So if you want to represent a number such as 23, then you would represent it as 10111 in the binary system. And the reason for that is that if you add these weights along with the digits, so this is 1 times 16, that is 16, plus 1 times 4, that is 4. So 16 plus 4 is 20. Similarly, this is a 2 and this is a 1. You add up all these things, that represents 23 actually, right? So here, for instance, this number is 8,732,937,309, right? So notice that every digit has its weight, and there are some possibly short names for specific digits or specific weights, such as a million, billion, so on and so forth, right? Okay. Now, in contrast to these two systems, the Roman system is not a position-based system. It essentially uses the letters I, V, X, L, C, D, and M, right? And these X represents a 10, L represents a 50, C represents a cent or 100, so on and so forth. Now Lx stands for 60 simply because L is a 50 and X is a 10, so you add them up, that's 60. Similarly, V11 stands for 7 because V is 5, these are two ones, so you add up, it is 7, right? So that's how you can think of numbers in the Roman system actually. Okay, so as we were discussing, positional means that they associate a value to a digit based on its position. So decimal, binary, octal, hexadecimal, you can think of a base 12 or you can think of a base 24, whatever you can think of, so long as you know what are the digits, and you can represent any number using these digits actually, right? So these are called positional systems. Non-positionals do not have such an association. For instance, even the unary system does not have any such association. Here in the unary system, when you want to write 6, you will simply write 6 ones, 1, 1, 1, 1, 1, 1, right? Okay. Now, let us see why we are discussing this example. The basic idea is that in most of the systems, or in every system I should say, it is possible to do operations on these numbers, right? The operations we can think of are addition, multiplication, subtraction, so on and so forth. Let us focus our attention on addition and multiplication, right? Now, the point we want to illustrate is that depending on the kind of number system you use, the nature of the operation will be either very simple or very complicated or something in between, right? So we will want to kind of bring this point out that depending on the number system, an operation may be difficult or easy, right? So let us consider addition first. And in the decimal system, we all know that we add digit wise. What does this mean? It means that if you have a carry of x from digit as position k to k plus 1, it is equivalent to a value of x times 10 to the k plus 1, where k is greater than 0, right? So for instance, when you add 87 along with 56, you know that there will be a carry of 1 from the units position, and that gives the result as 143, right? So that's how we do addition in the decimal system. Now binary system is equally similar. Instead of having carries weighted with 10 to the k plus 1, you will have carries weighted with 2 to the k plus 1, so you add it to the next digit on your left. Unary system is very interesting. I mean, if you want to add, suppose you want to add 6 and 4, or as shown here, you want to add 4 with 5, you simply copy these 5 ones and then concatenate with these 4 ones, resulting in the addition of 4 and 5, right? So here there will be 9 ones simply, right? So it's also kind of easy, right? You just have to count how many ones are there in one of x and y, and just copy so many ones to the other number, either to the left or right, doesn't matter actually, because all are ones, right? And there are no weights, right? Okay, so to add two numbers x and y, create a number that contains the number of ones in both x and y put together. That's how we add. In fact, that's how we learned addition also, right? In high school, when we want to add 4 and 2, or not in high school, maybe primary school, you want to add 4 and 2, you will write 4 ones on the right of 4 and 2 ones here, and then you copy these 2 and those 4 and make it 6 essentially, right? Okay, right. Now, I'm sure that most of us never attempted this, trying to add in the Roman system. It is doable. It is a bit complicated though. Let us see how that can be done. You have this following procedure to add two numbers in the Roman system. The idea is that you write the numbers side by side. So you have 32 and 67. So this is what I mean by writing these numbers side by side, just like the unary system did, right? But then in the Roman system, though we didn't mention it explicitly at that point, simply because we have some background on this, you don't write an L before or to the right of ones actually, right? I mean, and then have x's here. So this is not a proper number in the Roman system, right? So you may write 1 before an L or 2 ones before an L, but not certainly all this before an L, right? Because of the values attached with L, X, and so on and so forth, you want that L's are at the leftmost position possible, right? So we have to somehow rearrange this number or this format to reflect the correct representation. So what we do in this case is first arrange the letters in decreasing order. So that means you bring the L to the front, all X's together, then the V, then all the ones, right? So there is one L, 4 X's, 4 ones, and a V, right? Then we do some simplification, and the simplification means that you try to group together all x's, and if there are 5 of them, you make it a C, you make it an L, and if there are 2 L's, you make it a C, because 250s is an 100, so on and so forth, these kind of calculations. So here what we did is 4 x's can be converted to an L with x on the left hand side, right? So in general in the Roman system, if you recall, a lower number to the left of a higher number will indicate a subtraction, right? So this XL is equivalent to 40, right? Similarly, this V and 4 ones is actually 9, which can be represented as also 1 and x, right? So 10 minus 1. So you get XC1X simply because this is an L and this is an XL. So you could also combine these together. This is a 90 and that is also a 90, right? So you get this 99 as the answer, which kind of tallies with our regular decimal addition, right? And sometimes you have to keep on doing this simplification step so long as you can still simplify these symbols by grouping them together, right? Okay. Now it turns out that because whenever you simplify, you reduce at least one symbol length, you will end in a finite amount of time, right? So you cannot go in circles, right? I mean, when you simplify, you will end in a finite amount of time, but that may not be so easy to determine. You just have to repeat it till convergence. Okay. Now, these are the rules that I was mentioning earlier. You write 4 ones as IV, 4 x's as XL, so on and so forth, right? So of course, what if your original number itself has one of these complicated things like a 64, right? So you write it as LX1V. Now, when you want to do the addition, you may as well replace this 1V with 4 ones initially. Later on, during simplification, they may as well be absorbed without much trouble, actually, right? Okay. So that is how you can add in the Roman system. You may feel that by the time I described itself, it's a bit complicated. In fact, it is because of the whole unpredictable sequence of things you have to do. You have to simplify it till it cannot be simplified any further. So there are such troubles, actually, right? Okay. Now let us see what is the deal with multiplication. Typically, I mean, either by chance or by definition, most often the simplest algorithm to multiply is to actually think of it as a sequence of additions, right? So you want to consider multiplication, then it is achieved by repeated addition, right? So the tables we learn, essentially all these are, you could model it as repeated addition. So 3 times 4, you could as well add 3 4 times to itself to get the required result, actually, right? So that is what we mean by the decimal system approach, right? So you repeatedly add these numbers and you'll get the result. Now what about Roman system? Can you still multiply Roman numbers? Well, you can do, but it is much more complicated than addition. There are certain rules again. So how you multiply with a 10 or how you multiply with a 5, so on and so forth. So one way to understand this is to first multiply with a 10, then a 50, then so on and so forth, depending on what are the symbols in your number, and then group all of them together and then add them, actually, right? So that is one possibility. Okay. Now, so putting together this addition and multiplication itself, it is clear that we are looking at 2 things. One is the so-called representation efficiency, right? So how easy is it to write a number, and the other is the operational efficiencies. How easy is it to perform an operation in this number system, right? So let us look at these 4 systems. 1 is Roman, 2 is unary, 3 is decimal, and 4 is binary. Notice that the further to the right you go, the better the efficiency. The further up you go, the better the operational efficiency in this plot, right? So, well, if you think of decimal system, I want to say that it has the highest representation efficiency as well as operational efficiency. That is no wonder, because that's what we are using also, right? And the only reason computers use 0, 1 instead of decimal is due to the extra power required to drive 10 digits instead of 2 digits, right? If you can drive 2 digits and still get things done, it actually consumes less power than driving 10 digits across wires. That's why we use binary also. That's one way to think about it, right? So that's why I think that the decimal system has the highest operational efficiency as well as highest representational efficiency. Now I want to put the binary system maybe along this 45-degree line with respect to the decimal number or the decimal system, simply because addition and multiplication still mean the same thing in decimal as well as binary, but representation is slightly cumbersome because you have large things to consider for the smaller. So let us say even earlier, for writing 23 you could use only 2 digits in the decimal system and you needed 5 digits in the binary system. You could also relate these two quantities by some mathematical formula, but essentially the binary system will take longer space than the decimal system. So I want to keep that representation efficiency a little bit on the lower side, right? And you may ask, why did you also reduce the operational efficiency? This is simply because the longer the numbers, the bigger it takes to simply do the calculation by hand at least, right? So that's the motivation here. Now think of this number 1 sitting down here. That is the Roman system. You saw that it is very difficult to operate using these Roman things, but I would claim that even representation is not also very easy, simply because of the meaning the symbol carries changes according to its position to the left or right of a higher numbered symbol, right? So an XL is different from LX, right? So that's something it's not very easy to kind of take it into account. So I also want to say that the Roman system has very low representation efficiency and a very low operational efficiency. Somewhere in between is the unary. It's not very efficient in terms of representation, simply because again you have to write lot of ones. So if you want to write some 123, there will be 123 ones, right? So that's not very easy. But operation, it's okay. I mean, if you want to add two numbers, you just concatenate one to the another, right? Multiplication, we'll think about it separately. But at least it's not as bad as Roman numbers, because there are not too many rules to think about it, right? So that is my take on this. Okay. Now, I want to also show you that there are other such systems which are not in use today. You can also, here you may find things that are very interesting from the web. For instance, what kind of representation did the Egyptians use, or did the Mayans use, or think of any civilization and see what kind of number systems they used. There are particular mechanisms. Every civilization had its own representation and things to do arithmetic with, but some things that survived are probably the decimal and the Roman, actually, right? Okay. Now, you can also think of other representation formats that are either not positional or not to do with symbols, right? So these are these hybrid systems one can think of. One quick example is to think of a number being expressed uniquely as a product of primes, right? So that is, you could claim that that is my representation, right? I mean, I want to factor the number, I want to store it as a product of primes, and I will simply probably store the exponents as well as the bases, right? Okay. Now, you can see that in that representation, it's very easy to multiply, because you just have to add the exponents, right? So if you have 2 to the 3 and 3 to the 2, then the product is simply 2 to the 3 and concatenated with 3 to the 2, whatever its value is, right? But then it's not very easy to add, though. I mean, in this case, consider 2 to the 3 and 3 to the 2. I don't know what you get when you add these two quickly in the same representation, right? So you may have to do some number factoring, so on and so forth, which is not very easy, right? So that's another system that you can think of. And I want to show you that not only multiplication, this system has an advantage which no other system can possess in certain operations. So that operation is actually GCD. Let me take you to that slide. Right. So this is two numbers x and y represented as a product of primes. You don't need that k equal to r. One of them could be bigger. In this case, possibly r is bigger, right? So you have these primes and their exponents for y as well as for x, right? Now, by the definition of GCD, it holds that the GCD of these two numbers is simply these primes with the minimum exponent in each case, And you can also see that in this case the LCM will be simply the primes with the exponents as the maximum of these numbers, right? So if you are given numbers in this representation, it's very easy to do multiplication, GCD and LCM, but very difficult to do addition, right? So in a way, it also depends on the operation that you want to consider that will dictate the representation that you should use, right? But then for most operations, it turns out that there is an algorithm for even decimal numbers or binary numbers that can compute the GCD very efficiently. So we probably stick to these decimal or binary representation only because most operations are very efficient in this two formats. I mean, you could also add hexadecimal or other things to this collection, but essentially in a way, the positional ones actually score over the non-positional ones, right? Okay, so here for instance, you know this Euclid's algorithm which can compute the GCD very efficiently. Efficiently meaning that though it is not as simple as doing it in the case of prime number formats, it's at least much simpler than Roman numbers, for instance, right? Okay. Okay, so I want to also motivate you further. You may think of, well, what is the big deal? We're just dealing with numbers, and there are computers that can actually crunch numbers very quickly. But you should also notice that these days, there are applications which require us to work with very large numbers, say of the order of hundreds of digits, say 200 digits or more, right? One good example is the so-called RSA crypto system, which essentially is used in many of our online transactions also. So whenever you see some bank website or other financial websites where you do money related transactions, you should remember that there is a lot of number crunching that is going on behind the scenes, including possibly the RSA style number crunching, right? And here, even to process such large numbers, computers have a lot of difficulty because it is one thing to be able to do operations on things that fit into one machine word or slightly beyond that. Once numbers cross these limits, it is very difficult even for a computer to be able to do arithmetic on such large numbers very quickly, right? So that is still a problem of huge practical interest. I believe that there is still scope from improvement in that direction. And in fact, people are working in that direction actually to reduce or to be able to do fast arithmetic on large numbers, right? Okay. All right. So one can think of immediate take-home exercises such as trying to implement some of the algorithms that we are discussing this lecture. For instance, how to add Roman numbers or how to multiply Roman numbers, so on and so forth, right? Okay. Yeah, so I do want to acknowledge some people here. So some online sources about Roman number system. My knowledge, I mean, in these slides is from, I don't remember the references, but you could always Google for it, type Roman arithmetic or whatever, and you will end up somewhere else, right? And also one student, Pranav, who was responsible for this topic to be developed in this fashion. His idea is that number is a data structure, right? I thought that's good, and I wanted to see how far one can use this idea to illustrate or motivate the whole subject matter of data structures, right? So thanks to him also, and that's the end of the lecture, right?